Hello, and welcome to the next session in my webinar series on C++ Standard Template Library by example. Today, we're going to finish off our discussions of C++ STL functors. Yesterday, we provided the conceptual foundation for functors with our discussion of function pointers and pointers to member functions, but now we're going to actually talk about the functors themselves. So as always, let's take a look at what code we're going to examine, and then we'll jump right into it. So I'll share my screen here. As you can see, the code we're going to look at here is in my C++ STL S-08 folder, and it's in the 8.2 and 8.3 subfolders. And this, of course, is all on my GitHub repository. So let's go ahead and take a look at the code. First of all, just to recap, a functor or a function object is an object that can be called as if it were a function. And the way it does this, of course, is that it overloads operator function call or method call. And there's a whole pile of functors that come out of the box with STL that we'll take a look at here shortly. Things like arithmetic operations like plus, minus, and divides, things like relational operations like less and greater, as well as some of the more esoteric logical operations like logical and logical or. If you want to create an object that behaves like a function, you just need to be able to define the operator function call, and that's an easy thing to do. And you'll see that with C++ lambda functions, which we've touched on briefly and we'll explain in more detail later, you can do some really cool things without even having to define a full-blown functor class. So you can actually use lambda expressions to define these functors essentially in line. Functors are an improvement over C++'s traditional function pointer mechanisms that we examined the previous day. While you can still use function pointers if you want, and I'll show you some cases where you can switch back and forth between function pointers and functors, the ability in C++ STL to be able to optimize functors by using inline method expansion, as well as the ability to be able to store state in the functor objects, makes them in many ways a lot more desirable than using the more traditional pointer to function technique that comes from C. So let's take a look at a very simple example. This is a very simple function object. It's a stateless functor because it doesn't store any state inside the object itself. And as you can see, we have a class called simple functor object. The name gives away its fact it's very simple. And all it does is it basically defines operator function call with one parameter, and it simply returns that parameter. So it's kind of a mindless example, but it just is there to get us started syntactically. Then down below, we see how you can use this particular functor. We define a functor called a functor of type simple function object. And then we can go ahead and call it as if it was a function call. We can say a functor, open paren 5, close paren. And that looks like a function call, but in fact, it's actually calling this method on the simple function object. Or if we want to be a little bit more verbose, we could also call it with this syntax. So you can say a functor dot operator function call, open close paren, and then pass the parameter in that way. I would very rarely, if ever, write code like that, much more likely to write code like this. And of course, in practice, I'm also likely to use functors that are a heck of a lot more interesting than the one we just showed. So this is just here to kind of whet your appetite and get us started. So since that was pretty simple, let's go ahead and take a look at another example. So this is the second example we're going to look at. So it turns out that there's a whole pile of functors that come out of the box with C++ STL. And these are all found in the functional header file, and they all derive from certain base classes. So from basically there's binary function and unary function base classes. And so those are kind of the building blocks upon which the other functor classes are derived. So let's take a look at some of the examples of functors that come out of the box with C++ STL. So as you can see, the first chunk here are all the arithmetic operations like plus and minus and multiplies and divides, as well as the ones that are a little bit more obscure like modulus, which is the binary mod operator. Sometimes we joke that C and C++ were attempting to use all the funny characters, all the special characters on the keyboard, and they certainly did that nicely with the operations they define. The functor classes, as you can see, are a bit more intuitive in terms of the names that they provide. Then there's also a bunch of relational operations or comparison operations like equal to, not equal to, less, greater, and so on. And they have corresponding behavior similar to the operations you can write in code. Now, at this point, you're probably going, why do we have to have all these classes when there's already operators built in? And the basic reason for that is that this allows us to be able to parameterize these functors in algorithms and in containers in order to control and strategize their behavior. And then lastly, there's also a bunch of logical functors like logical and, logical or, logical not. I don't tend to use these very much, but they do exist. So as I mentioned before, these are the functor base classes. So you can see we have binary function, which takes two parameters for arg1 and arg2, as well as the function template parameter for the result type. And then it goes ahead and actually defines names for these things. These are all examples of traits, by the way. So first argument type, second argument type, result type. Those are all things that come along for the ride as traits of a binary function. And it probably would not be much of a surprise to recognize that the plus operation is a binary function that's parameterized by TTT. So it's going to work on the same consistent types. And you can see here, just as an example, the operator function call on the plus functor takes two parameters by constref and then adds them together and returns the result. And I think, it'll come as no surprise that the minus and the multiplies and the divides functors also do the same sorts of things, just with the corresponding subtraction, multiplication, and division operations. So no real surprises there, other than the fact that we're giving a name for something that will end up turning into an operation on parameters. Here's an example of a unary functor. So this is the unary functor struct, or the unary functor type creator. And as you can see here, it takes a single argument and has a return value. And an example of a unary function would be negate. So you can see negate inherits from unary function, gets its parameters, it rather gets its type traits, and then it defines operator function call to negate the result that's passed to it. All right, well, it still may be a little bit mysterious as to why we're doing this kind of stuff. So let's take a look at some examples that will make it more clear. So here's an example of a user-defined functor that extends the unary function template. So here's a unary function, and we define a unary function called isEven. And that's a great example of kind of a predicate. And if you take a look here, you can see that isEven takes, it defines a single method, the function call operation. It takes an int I, and then it goes ahead and it says, cast the result of the I modulus 2 negated. So what this is trying to say is this an even number? And if I mod 2 negated is true, then that will be treated as true. The result of isEven will be true. Otherwise, it will be false. And you can see that the parameters that are passed into the unary function template are int, because that's the type that we're passing as the parameter to operator function, and bool, because that's the result we're returning from operator function call. Okay, so far so good. So down here, you can see how we're actually going to use this particular functor for a nice, simple little example. So we're going to define ourselves a vector, and then we're going to go ahead and push 20 numbers into it, 1 to 20. So we go ahead and push those things into the vector. And then we're going to go ahead and print the results of the vector, and I probably should be using auto here just to be more abstract. I think you probably knew what int was. And then down here, we're going to go ahead and call the COUNTIF algorithm. And we're going to take a look at the code for COUNTIF in just a moment. But before we look at the code, what it's going to do is it's going to iterate through the range from the beginning to the end of that vector. And for every element there, it's going to call the isEven functor. And as you can see, isEven is an anonymous, what isEven is doing is the isEven constructor is creating an anonymous object of the type up here, the isEven type. So we are going to pass an anonymous object into COUNTIF. And then that anonymous object's method call operator will be applied to each value in that range. So let's go ahead and take a look at the code here. So here is the COUNTIF algorithm coming straight out of the STL algorithm header file. And you can see what it does is it's parameterized by an input iterator and a predicate, which of course will be the functor. And so it takes a range from first to last. That's the iterator range. That's what we saw right here, from AVEC begin to AVEC end. And we're going to crank away through this thing. And every step along the way, for each element that's in that range, we're going to apply the predicate. And of course, that predicate is going to be an anonymous instance of the is-even functor. So we make an anonymous instance that gets passed by value into COUNTIF as the third parameter, as the predicate. And you can see that what it does here is it calls the predicate using the function call operation on the predicate object, on the functor. And what will happen is it'll pass in the parameter that's pointed to by the iterator that we're currently walking through, so star first. And in our case, it's an int, and it'll return either true or false. Is it even or is it not? And as you can see here, if it returns true, then we increment the count by 1, otherwise we don't do anything. And when we're all done, we go ahead and return the value that we've stored here. You can also see how the COUNTIF method goes ahead and defines something of type iterator traits, input iterator difference type. So it's going to go ahead and create essentially an object that it can use to increment each time through. So armed with that knowledge of what the functor does, and armed with that knowledge of what COUNTIF does when passed a functor as a predicate, let's go ahead and run the code. And you'll see here that we're going to give it the numbers 1 through 20, and it comes back after calling COUNTIF and says 10 numbers are evenly divisible by 2, which of course is correct. Now you'll notice it didn't say what those 10 numbers were, but obviously they're the ones that evaluated to true using the is-even predicate. Okay, so that's a very simple example of writing your own functor and then passing it to an existing algorithm. What we're going to do now is we're going to take a look at some other examples that are a little bit more interesting. And the reason why they're interesting is because they're going to use a bunch of the built-in functors that come out of STL. And we're going to focus here on the arithmetic functors. We'll look at some other ones later. And most of the arithmetic functions are binary operations that return the sum, the difference, the product, or the division of the first argument and the second argument. And so obviously binary as usual means 2 parameters, and unary means 1 parameter or 1 argument. So here are a bunch of the different types. Probably should use a font that's a little bit more forgiving. Richard Hendricks would not be happy with me because I'm probably using, actually he would be happy with me because I'm using tabs, not spaces. If anybody's here has ever seen the classic Silicon Valley TV show, there's a wonderful episode where the main protagonist, Richard Hendricks, gets mad at his girlfriend because she uses spaces and he uses tabs. And he can't possibly understand how anybody could use spaces instead of tabs, which I think is funny. I'm actually a spaces person myself, but be that as it may. Okay, so here is our program. We're going to define a vector that has a bunch of floats in it. And I guess, let's see. I guess in this particular case, they're treated as floats, but I could give them different numbers. I could say 1.2 and 3.7 or so on. I just gave them integral numbers that get promoted to the corresponding floats. So now what we're going to do is we're going to go ahead and do some operations that demonstrate how the arithmetic functors work. And we're also going to demonstrate a few other things too that we'll talk about in more detail later. So one thing we're going to demonstrate is a couple of transform algorithms, which are super cool algorithms in STL. And we're also going to start kind of giving a little foreshadowing of something called a binder. And we're going to talk about binders in more detail next time we get together. But for right now, let's just focus on a simple use case. So what we're going to do here, as the comments say, is we're going to take every one of these values and we're going to march through them from beginning to end. And then we're also going to take the same values and we're going to march through them from beginning to end. And at every step along the way, in those 2 ranges of values, we're going to apply the multiplies binary operator. And what that's going to do is it's going to multiply the values together, and then it's going to store them somewhere, and it's going to store them on top of themselves. So we're basically going to multiply all the floats in the vector by themselves and store them into the vector, I should say store them back into the vector. So we're going to store them right back into the vector from where they came. Now, we don't have to do that. We could put them into a different vector, but we're going to put them in the same vector just for kicks. And after we're done, we're going to go ahead and print the contents of that vector out using our copy trick with the begin and end iterator and the OStream iterator adapter to write it to the output. Then the next thing that we're going to do, and I think just for kicks, I'm going to get rid of this new line and put a space because it's a little easier to follow along if I do that. Then the next thing we're going to do, so now we're going to take all the contents in the vector. We've already multiplied them by themselves. And now we're going to divide all the contents in the vector by 3 and then store the result back into the vector, the same vector. And the way we do that is we start using the 4-parameter version of transform as opposed to the 5-parameter version of transform we used before. And the 4-parameter version is similar to the 5-parameter version with 2 main differences. First of all, it only has a single range, not 2 ranges. And it also takes a unary functor, not a binary functor. And in this particular case, the functor that we're going to do is we're going to take the divides functor, which is a binary functor, and we're going to bind its second argument to the value 3, or to the float 3.0. And so what that's going to do is that's going to go ahead and divide all the floats in the vector by the value 3, and it'll update the vector in place again. So let's say, and store them back into the vector, so into the same vector. And then we print the results out. And again, let's make things a little bit more legible by writing the code like this. Okay, so that's what we're doing. Let's go ahead and run it and see what the results are, and then I'll explain it a little bit more. So you can see we took the original input, which I probably should have printed out the original code. So that's super easy to do with STL because we just go ahead and copy the code up here and reformat it just a tad. And now let's go ahead and rerun this so you can see the first round of results. So the original values were 1, 2, 3, 4, 5. And then we went ahead and multiplied them by themselves. So we ended up with 1, 4, 9, 16, and 25, because that's multiplying them by themselves. And then the last thing we do down here is we go ahead and divide everything by the float value 3.0. And what we end up with is the result of dividing all these things by 3 within the precision that C++ floating point arithmetic will permit us. So that's basically what's going on. Let's take a look for kicks at the transform algorithms. We can peek into their code. We'll talk about transform again later when we actually get into the algorithms part of the course. But for right now, let me just give you a foreshadowing of what's coming. So here's the transform algorithm. You can see it takes quite a number of parameters. It takes an input iterator, and it takes 2 input iterators. It takes an output iterator and a binary operation. That's the templates that are passed into it. And then you can see that it has a lot of parameters. It has an input iterator called first and an input iterator called last, and those are first one and last one. We then have another input iterator called first 2, which is expected to have the same range as first 1 to last 1. And then we take an output iterator called result. For this particular example, we put the results in the same vector we were manipulating. So we were updating the vector in place. But you don't have to do that. You could always use pushback, or you could put it into another vector and so on. And then we pass in a binary operation, which is obviously going to be a functor that takes 2 parameters. So let's take a look at how this is going to be implemented for basically for the beginning of this thing, for first, while we don't hit last. We're going to go ahead and call the binary operation, which is our functor, passing in first 1 and first 2's value by dereferencing them. That's going to apply the operation, and then we're going to store the result in the dereferenced result output iterator. Now again, looking back at our example, you can see how we did everything in place here. So we went through the range twice, so we are multiplying the objects by themselves essentially, and then we store the results into the same vector that we're getting the values from. And that all works fine because of the order in which these things take place. First, we do the operations on first one and first two, and then that gets stored in result. And by that point, we're ready to move on to the next element in the range. And that's exactly what we do. We go ahead and increment first two, and we increment first one, and we also go ahead and increment result. So we're just marching down one at a time. And when we're all done, as is often the case with the STL algorithms like copy and so on and transform and other things like that, we go ahead and pass back the result after doing the increment on each one. So you could kind of chain these things together if that made sense for your particular use case. Okay, so that's the 5-parameter version of transform. Let's go take a look at the 4-parameter version of transform. So here's the 4-parameter version of transform. It takes similar types, except it takes a unary operation, not a binary operation. And likewise, it has a bunch of parameters. You can see it takes a first input iterator to a last input iterator. It takes an output iterator to put the result, and it takes a unary operation. And what it does is it marches through that range from beginning to end, and this time it applies the unary operation on each element that's being iterated over in turn and stores the results back into star result. And then it finally returns that at the end. So this version uses unary operations, whereas the other one we looked at, the one that I think is right here, uses binary operations. So those are examples of transform. We will see that transform is a very powerful algorithm. It's kind of like map, if you're familiar with Java and Java streams. It's kind of along the lines of the map operation. So it takes its input, does something to it, and returns some output. Okay, we have one more example to go. And let's go ahead and look over here to find that. I believe it's this one. So now what we're going to do is take a look at some of the relational operations that are supported by the STL. And as you can see, there's the obvious ones you might expect: not equal to, less, greater, less than, and equal, greater than, and so on. So these are all the things you'd normally expect to have with C and C++ arithmetic operations, just defined in terms of functors, so we can parameterize algorithms or containers with these. As you can see here, you can also create your own if you want by basically inheriting from unary function or binary function, as we had talked about before. So this particular example is kind of fun. What it's going to do is it's going to have a string, and that string is going to have spaces between each of the words in the string. So the string itself is called spaces in text, and indeed that's what it has. And what we're going to do here is we're going to print the string, and then we're going to call a very interesting method called remove if. And remove if is going to go through the range from beginning of the string to the end of the string. And every step along the way, it's going to remove anything that happens to match the predicate that's passed in. And the predicate here is a space. And so we're going to use this binder, this bind second binder adapter. We'll talk more about that next time. And the binder adapter here is used, as was the case with the previous example with transform, to convert a binary functor into the expected unary functor, because remove if expects a predicate, which is essentially a unary functor. It expects one value. So what we're doing here is we're saying, take out anything in this range that's a space. So that's why we're removing the space. And what we get back from this is a new iterator to the end of this string that no longer contains any of the characters that we've removed. And I'll show you how remove if works in a second. It's kind of interesting. Now, we're going to do two things here. First, we're going to go ahead and just print out S again after we've removed the values. And you'll see that it actually hasn't removed them. They're just at the end, and you'll see what that means when I look at the code with you in a second. But then if we really do, in fact, want to remove them, we can use the erase call on string, and we can pass in the new end, which is what we get back after we remove stuff, going up to, but not including the old end. And so that actually erases them from the string. So they're no longer considered part of the string. So when we print the final string, we'll get the version that actually removes all the spaces and doesn't leave anything else in its place. Let's go ahead and run the code. You can see here we get the original string says spaces in text. Then after we do the remove if and get the new end, when we print the old string, we get spaces in text xt. And of course, the xt here corresponds to these two characters left over at the end. And that may give you a hint as to what remove if is actually doing. And we'll look at its code in a second. And then after we erase everything, now we just say spaces in text. So the final xt has been eradicated or erased from the end of that particular string. All right, let's go look at remove if's implementation and see if we can make sense of what it's actually doing. And it's doing some interesting things. So first of all, let's kind of take a look. It's one of the longer STL algorithms we've looked at so far. So you can see it's given a forward iterator, which means we can read to it and write to it, and it's given a predicate. Those are the template parameters. And then remove if takes two forward iterators, one to the beginning of the range, one past the end, and the predicate. And the first thing it does is it goes ahead and it says, does this particular predicate match anything at all in this range? And so it uses another STL algorithm called find if. And so what find if does is it goes through a range from beginning to end with a predicate, and it looks for the first match. And the second it finds a match, the second the predicate returns true, it returns an iterator to where it returned true. So we use this to kind of make the code a little bit shorter and kind of leverage existing functionality that was added to STL. So if what we get back here is something that doesn't equal the last iterator that was passed in as a parameter, we know that there was in fact one thing that matched, at least one thing that matched. So what we do then at that point is we go ahead and we start from where we left off when we found the match, and we're going to go ahead and increment that by 1, and we're going to keep going till we find the end. And every time we go through here, what we're going to do is if there's a match, we're going to ignore the item. If there's a match, we're going to, removing if we have a match, we're going to overwrite the item. If there is no match, we're going to ignore it. It's a little bit complicated to think about. So in other words, if the predicate doesn't match, then we go ahead and copy the contents over. But if the predicate does match, we're going to ignore it, so it doesn't get copied over. And so what we're basically doing whenever we find a match is we're copying over that element in the underlying container using the iterator as a way to control access to it. And you can see here that because this is C++ 17 or whatever the compiler is, we can use the move semantics to do that move very efficiently without having to do a lot of unnecessary copies. So that's some cool stuff that's brought along for the ride by using newer versions of C++. So what we're basically doing, whenever we find something that matches, we're sliding stuff over on top of it and, quote, removing it. But what happens when we get all the way to the end is we return a new iterator to the place we left off when we reach the end. But anything to the right of that in the container is going to still be there. And so if we don't want that to be the case, because remember we split everything down, if we don't want those things to be there when we're all said and done, then we have to go in and we have to erase them by using the erase method, passing in the new end, which is what came back from remove if, going up to, of course, but not including the old end. And that will then update the container itself. You might ask the question, why can't remove if update the container? Well, the reason, of course, is that remove if doesn't know anything about the container. It only knows about the iterators it's passed from the container, which it doesn't have a way of distinguishing what the actual type of the container is. So after we do remove if we want to chop the container to not include the elements that were at the end, then we go ahead and call erase. And this becomes even more clear, and we'll see examples of this later, when we talk about using remove if and other remove operations when we're dealing with built-in C-style arrays, where you really couldn't remove them without doing some other fancy footwork because there's no way to erase them because they're part of the array. Okay, so those are the things that I had wanted to talk about today. What we're going to do next time is we're going to go into more detail about the many, many function adapters that are available in STL. And we'll talk about the binders. We talked a little bit about binders today. We'll talk more about binders next time. We're also going to talk about negators, We're going to talk about basically the pointer to function and member function adapters and so on, some of which are really cool, but some of these things are a little bit more esoteric. So I think the key thing that we'll do when we get together next time is we'll go through the binders and then the gators. Those are actually very, very important because you can use them to chain together sequences of essentially functional programming operations. And they can actually get quite involved. And that's one of the things that makes STL so powerful, is all these things can be composed together and the compiler can optimize the heck out of it, because under the hood, a lot of these things are just inline function calls that the compiler can compose and then optimize and compress. So it's very efficient, very cool, very abstract, and it's yet another great example of C++'s support for zero overhead abstraction. So thanks again for joining. If you enjoyed the content, please like, please subscribe, and feel free to follow me on Twitter.